All right, so recording is started. So basically, if I what happened?
Sir, for eigenvector and eigenvalue, you will only give us 2 by 2 matrices, right?
What is wrong with 3 by 3?
I'm just asking, Mister.
For you, 3 by 3. For all others, 2 by 2.
Huh?
For NASA, 3 by 3.
Huh?
For others,
You
two by
think I
two.
shouldn't ask, right?
Yeah. Final exam review, fall 2024-25. So basically, let me just break down, which we had in the email as well. I said we will have from 2.2 and 3.3, we have inverse of a matrix. Inverse of a matrix has two methods. One we studied in 2.2 and one we studied in 3.3. So one question you can expect, like finding the inverse of a matrix, inverse of a matrix A inverse, right? So you can use any method. I did not bound you to use this method. So in 2.2, we had um, row reduction algorithm to do that. So you can use row operations algorithm. Um, so what was that? Row reduction algorithm is that you write A, your matrix given A, and you write identity matrix with it. You write two matrices together, and then you use row operations to change the first matrix to identity. So whatever matrix is given, you will start making this one, make 0, 0 below that. Then you go here, make 1 and make 0, 0 above it. And then you have 1 here and make 0, 0 above it, right? So once the left side, this A matrix becomes identity, you keep on using the row operation on all of them because you started from identity. That identity will become something else now, right? There will be some number. It will not remain identity because you have been using row operations on them. So this second portion automatically becomes A inverse. So this is the algorithm basically, that you have to write A along with your identity matrix. The left matrix A, you have to make it identity by using row operations, but keep using the row operations for the whole row, not only with 3 by 3 matrix, but all these columns as well, 6 columns. So then the last 3 columns, they give you the inverse matrix. This was we studied in 2.2. In 3.3, we had a formula to find the inverse. And that formula was A inverse is equal to 1 over determinant of A into adjoint matrix of A. So that formula is 3.3. So you can use any method here. Here, adjoint matrix is basically the transpose of the cofactor matrix C11, C12, C13, C21, 22, 23, like that. 31, 32, 33. And the transpose of that. So when you take the transpose, it becomes C11, 12, 13. The first row becomes first column. The second row becomes second column. The third row becomes third column. So this is your adjoint. So if you divide this adjoint matrix by the determinant of A, that gives you the inverse. And of course, you get the same inverse. There will be no difference. Where this Cij is the cofactor, ijth cofactor. We call it the ijth cofactor of matrix A, right? Or you can say that it is a cofactor for the element of Aij. If you pick Aij, it's the cofactor. So if this is A11, what you do, you remove the row and column, of A11 and the remaining point here, this is the determinant. So you pick the remaining amount, you remove first row, first column, remaining matrix, this one, you take the determinant of that. So C11 will become the determinant of these three things here. A22, 23, 32, 33. So A22, 23, 32, 33. So you have to do it with all the elements. If you go to the second one, remove this row and this column now, you will get a number from here, a number from here, number from here, and a number from here, and take the determinant. And this also gives you plus and minus sign. If the sum, this is plus, if the sum of row and column 1 plus 1 is 2, so that is even. So whenever the sum of row column is even, you get a plus. And the sum of row, if it is C1, 2, you will have a minus sign, because 1 plus 2 is 3, which is odd. And whenever you have odd number, you get a minus sign here. Okay, so for even you get plus, for odd you get minus. So that's how it changes the sign. So if I go to there were some notes on determinants, right? So you can see it here. That if you are finding the inverse, let's say, of this matrix, we had this inverse here, but I wanted to fix it. It's your cofactor matrix is basically C1112. It's not A11, A22. So here, what you will do, you will write C11. First of all, you will find the determinant. If the determinant is 0, of course, there is no inverse. So determinant has to be non-zero. So we know that we start with this 2, and then we remove this row column. So this 3, 4, and 3, 1, 2, 4. And then minus the second one, minus this is plus. And then this row and this column is gone. So 4, 4, 1, 1. 4, 1, 1, 4. And then plus the third one. This 4 is again plus. So this row and this column is gone. So 4, 3, 1, 2. That's how you find the cofactor as well. This is the cofactor of 2, right? But it is 2 into 12 minus 2, 10 minus 3, 16 minus 1, 15 plus 4, 8 minus 3, 5. So this is 20 plus 20, 40. And minus 45. So that is minus 5. So see, it's not equal to 0. So it means A inverse exists. If this determinant is 0, there is no A inverse. You can stop here. So now we will write C11, C12, and so on. So C11 is plus first one now. So C11 is exactly this one, 3, 1, 2, 4. First row, first column is gone. The remaining one is this. So that is 10. Then C12. C12 means negative. Why? Because 2 plus 1 is 3, negative. So it will give you negative number here. 1 plus 1 is 2, gives you positive. So now it is same 4, 1, 1, 4. Because now first row, second column is gone. C12 means first row, second column is gone. So you got 4, 1, 1, 4. Okay, so you got this one. So that is, of course, minus 15. And then C13. C13 means, again, it is plus, because 1 plus 3 is 4. 4 gives you plus. So now first row and third column is gone. So 4, 3, 1, 2. In determinant, we only do, in determinant, we only pick one row or one column and just write this is the determinant. But for cofactors, I have to complete all 9 cofactors. So if I remove everything again, so now you see, if I'm going to C21, C21 is minus because 2 plus 1 is 3, 3 gives you minus. But this is C21. So this second row and first column is gone. So now you will have 3, 4, 2, 4. 3, 4, 2, 4. So that's how you will complete 12. 12 minus 8 is 4 and minus will give you 4, right? And so on. So complete all of them. C22, C23, C31, C32, C33. So once you get all the values, you will write them as a cofactor matrix. So cofactor matrix is, so you will write cofactor matrix. Cofactor matrix is C, which is C11, C12, C13, C21, C22, C23, C31, C32, C33. Once you got that, then your adjoint matrix is the transpose of this one. So the first row will become first column, second row will become second column, third row will become third column. That is your adjoint. And at the end, you will just divide this adjoint by the determinant of A. So determinant of A was -5 in our case. And this matrix comes here. Divide all the entries by -5, you will get the inverse. So that is one way of finding the inverse that is given in 3.3. The other way was 2.2, which is the row reduction algorithm. So see here, one of them is done, but actually the matrix is A11, A12. This should be C11, C12, C13. These are all C. This is your cofactor matrix, okay? So this is C11, C21, C31, C12, C22, C32, C13, C23, C33. So you write all these here, you see, 10, 15, 5, first row, 4, 4, 1, second row, -9, -15, 6, third row. So that was plus, minus, plus, minus. So that is your inverse which you got. And now this is the exact thing which we did here. But because here it's A11, A12, that's not correct. It should be C11, C12, C13, okay? And with their minus signs. So keep minus sign here. Then this is minus, so -4. And this is minus, so this is -1. This is plus, and this is minus, plus 14. So see, these are the values that you are getting. I think in the same sheet, the other method is also given. They call it Gauss-Jordan method, but in the book, they wrote it row reduction algorithm to find the inverse. Row reduction algorithm to find A inverse. Okay, so sometimes they call it Gauss-Jordan method to find the inverse. It is the same thing. So here you see, I wrote the matrix on the left. This is the matrix A, right? And here we write the identity matrix. We write them together and then we look at this one. This is 1, make these two 0, 0. So see 1, 0, 0. And then this is 2, divide, keep this and make up and down 0. And then after that, you get 1 here and make up 0. So see, now the left side has become identity. But because whatever row operations I was using the row operation on the whole row. So this will change your identity matrix to a new matrix, and that new matrix is your A inverse. But don't leave your answer here. Write A inverse separately. Because they have given me A matrix, you see, A matrix is given. I use A and identity together to find the inverse. But once you got I into some other matrix, write this matrix separately and call it A inverse. At the end, you can check your answer as well. If let's say if you want to check whether our answer is correct or not, you can multiply A with A inverse. It will give you identity. If you multiply these two matrices, you will get the identity matrix. So this will show you that your answer is correct actually. So a couple of examples are done with row reduction algorithm, right? And a couple of examples are done with this 3.3 cofactor method. So whatever you want, you can use it, no issues. But on the other hand, if two matrices are given, let's say, if two matrices A and B are given, right? And you have to verify that A and B are inverses of each other or not. Then you will not find the inverse. Don't find the inverse. Just use this one. Then what will be the solution? Just multiply A with B. Two matrices are given, multiply A, B, right? You will get the identity matrix 1, 0, 0, 1, etc. It will be identity, depends on the order of A and B. If they are 3 by 3, you will get 3 by 3 identity matrix. If they are 2 by 2, you will get 2 by 2 identity matrix. Similarly, multiply B with A. Multiply B with A. And you will simplify, you will see that this will also become identity. So if two matrices are given to you and you need to verify that whether they are inverses or not, just multiply A with B and B with A, they will both give you identity. So this will verify that they are inverses. And if any one of them, if AB becomes identity and BA does not become identity, you can say that no, they are not inverses because both have to become identity. But when you find the inverse in this here, when you find the inverse to check whether they are inverses of or not, only one way is enough because here you found the inverse. So if you just multiply A with A inverse, it becomes identity. No need to check the other one. Okay. No need to check the other one. It will automatically be identity because you found the inverse here. So if one of them gives you identity, the second automatically gives you identity. No need to check that. But here I did not find the inverse. Here two different matrices were given to me. If I have to verify whether they are inverses or not, I have to show them both. AB is identity and BA is identity. So this was one of your questions. And then we had a Cramer's rule, right? Cramer's rule to find the solution. So that Cramer's rule is also given in 3.3. In 3.3, another thing is using Cramer's rule to solve the system, right? To solve AX equal to B, a linear system. If it is a linear equation, linear equations are given, you will write it as a matrix form AX equal to B. You will find the determinant of A. It has to be not equal to 0. Because if it is 0, you cannot apply Cramer's rule. So not equal to 0 means yes, go ahead, you can apply Cramer's rule. Because Cramer's rule formula uses determinant in the denominator. If determinant is 0, you cannot divide by that. So Cramer's rule is not applicable. So of course, if we ask that use Cramer's rule, then determinant will be non-zero definitely. Then we define A1B A1B means replace the first column by B. Replace the first column by B. See, A1 means first column by B and remaining column will remain the same. The second column will be the same. Third column will be the same. A2B means replace the second column by B and all other the same. B in the second column. So B in the second column, A1, A3, so on, they will be the same. So that's how you can keep on defining as many. If your matrix has 3 columns, then you will have 3 matrices here. A1, A2, and B will be in the third column now. If you have only two columns in your matrix, then of course I will only have A1 and A2. If you have four columns, then you will have A1, A2, A3, A4. Now find the determinants. After defining these matrices, define these matrices, three matrices, and then find their determinants. Determinant of A1B. Or you can write this determinant of A1B is this as well. It will be a number, of course. Then you will find the determinant of A2B. Determinant of A2B. And then determinant of A3B. They can be zero, no issues. They can be zero, non-zero. Any number can be there. Then Cramer's rule says that your first value x1 is equal to the determinant of A1 divided by the determinant of A. That's why we said determinant of A should not be equal to 0 because we are dividing them. X2 will be the determinant of second matrix divided by determinant of A. And X3 will be third divided by A. And if there is fourth one, then X4, 5, X5. But usually we are given only 2 by 2, 3 by 3 matrices. If it is 2 by 2 system, I will only have A1, A2, and only X1, X2 will be needed. If it is a 3 by 3 system, then I will have A1, A2, A3, and X1, X2, X3 will be the answers. A very simple rule is that the one question you can expect from here. So let me see in the book.
Sir, I have a ready example if you need.
Ready example?
Yes.
Which one is that?
2x1 plus x2 plus x3 is equal to 1. No, not from the book.
It
This
is
is from outside.
Is it from the book?
No, it's not.
It's not?
Yes.
Okay. So let me show you where these are. So see here, 3.3, this one. Right? So these are the Cramer's rule, 2 by 2, 3 by 3. So you can try one of them. You can try one, you can try 5 or 6, right? They'll give you some practice. No need to do this with S. Okay. So only from 1 to 6 will be enough. And these are the inverses, you see. Find the inverse using the adjugate matrix. Finding C11, C12 cofactor matrix. So pick one question from here. It will be enough practice for you. So you were saying example for Cramer's rule. 2x1
plus x2 plus x3 is equal to 1.
1.
3x2 minus x3 is equal to 7. X1 plus 2x2 plus 2x3 is equal to minus 4.
Correct.
So it's 2x1, x2, x3, 3x2 minus x3. Yes.
So here A is the coefficient matrix. 2, 1, 1, 0, 3, minus 1, 1, 2, 2, right? Only the left side, coefficient matrix. And B is the vector on the right side, 1, 7, minus 4. Because we are writing it as AX equal to B, right? So where A and B are given, and X is definitely your unknown vector, X1, X2, X3. So first you wrote the matrix form. And now first thing is that first see whether determinant of A. You can write like that as well, if that is 0 or not. So 2 into 6 plus 2. I'm doing it directly. If you feel you need more, you can write that 0 into 2 plus 1. So 0 plus 1, and then plus 1 will give you 0 minus 3. So see here, 2, this is gone. So I got 6 plus 2, right? 6 plus 2. And then 1, this is gone. So you got 0 plus 1. 0 into 2, minus into minus 1, so 0 plus 1. And then you got 1, this is gone. So you got 0 minus 3. So 0 minus 3. So,
So it's 12.
so that is 6 plus 2, 8. 2s are 16, minus 1, 15, and minus 3, 12. Right? So this is not equal to 0. Go ahead. This is what we needed. Now we will define A1B. So A1B means replace this B vector in the first column. The second column 1, 3, 2 is the same. The third column 1, minus 1, 2 is the same. Right? And now you can find the determinant of that as well. Determinant of A1B. So first we can write these three matrices, then we can find the determinant. A2B means the first row as it is, 2, 0, 1. Second row is replaced by B and third row as it is. Right? So see here, 2, 0, 1
I have
is
ready
the
answers.
okay, no issues.
So for the A1B, it will be 24. And for A2B, it will be 12. And for A3B, it will be minus 48.
Okay, so third column is the first column as it is, the second column as it is, and the third column is replaced by B. Right? So this is what we do. So if you find the determinant of A3B, they said it's 48. So you can check it. It's 24. So basically we will find the determinants. It will come out to be 24. Similarly, for the second one, if you find the determinant, should come out to be 12, and third is 48, right? So you can do it at home. Of course, after this session, you can just check it, it's minus 48. So after that, Cramer's rule says that, so therefore by Cramer's rule, I can write my x1 as the determinant of A1B divided by the determinant of A. So this is 2. X2 will be determinant of A2B divided by determinant of A. So it's 1. And X3 is determinant of A3 divided by 12. So that is minus 4. So 2, 1, minus 4 is the answer. And you can check this as well. It's optional, but you can check your answer. Check your answers, like if you replace 2, 1, 4 in your equations, 2, 1, 4, it should give you 1. So 2, 1, 4, 2, 1 minus 4, right? So 2 into 2 is 4 minus 1 plus 1 is 5, and 5 minus x3 is minus 4. So 5 minus 4 is 1. So first one is true. Then x2 is 1. So 3 minus 4. 3 plus 4 is 7. And x1, 2 plus 2, 4. 4 minus 8. 4 minus 8 is minus 4. So see, all three equations are satisfied. So it means it is good. So you replace it the right hand side. Replace it on the left, the right hand side, so you get all the equations. So it's a good thing to check your answers at the end. If you don't check it, it's not, of course, compulsory. But if you check everything is okay, then you can make sure that all our calculations are correct. So in chapter 5, 5.1 and 5.2, here together, there were two things. One was characteristic equation.
Mister,
Yes.
I have a question in 3.3. The book,
Okay.
the question 22.
Here.
No, in the book, there is question, the number 22.
3.3.
The question number 22. In the assignment. 70.
This one.
Yeah.
So here it is, find the area of the parallelogram. Area of parallelogram is just the determinant. Okay. If you have a vector here, right, and a vector here, two vectors are given, and these vectors are, of course, in column form. If let's say AB is this vector and CD is this vector, then you can complete the parallelogram like that, right? So this is the parallelogram basically. So what is the area of this parallelogram? It is the determinant of A, B, C, D. Means if you write first vector in first column, the second vector in second column, and take the determinant. And if it is negative, then you can take the absolute value of that. Okay, absolute value of this determinant. So if you look at this question, you have 0, 2, 5, 2, minus 3, 1, 2, 1. So you can, from these 4 points, you can make 2 vectors. I need just 3 points, not all of them, because 3 points will give you, if this is A, this is B, this is C, and this is D. I don't need D. From A to B, I can make 1 vector, and from A to C, I can make the second vector, but that's enough. Okay, so how we find vector A, B? Basically, it is you subtract the points x1 minus x0, y1 minus y0, if 2 points are given. So if you look at that question, 0 minus 2, 5 minus 2, 0 minus 2. This is 1 point, 0 minus 2, and then 5 minus 2. 1, 2, 3, 4, 5. 5 minus 2, this point. So these are these 2 points, 0 minus 2, 5 minus 2, and then minus 3, 1, and 2, 1. So minus 3, 1. This is minus 3. Sorry, x minus 3. Minus 3 and 1. So this is minus 3, 1. And 5 minus 2 minus 1. 2, 2, 1. Minus 3, 1, and 2, 1. So 2, 1 is 1, 2, this point. Right? So this is 2, 1. So see, it's a parallelogram. If you join these points, see, these 2 vectors are parallel. And if you join these 2 points, they are also parallel. See? So it is a parallelogram which they gave me. Now you can pick any 2 points. You can pick this vector. Let's say first vector, you can pick this one, right? And the second vector, you can pick this one. I just need these 2. So this vector will be subtract the points x from x. So 5 minus 0 and y from y, minus 2 plus 2. So this vector becomes 5, 0, right? This vector becomes 5, 0. And the second, this vector is x minus 3 minus 0, x values, and y values, 1 minus minus 2. So this vector becomes minus 3, 3. So these are the 2 vectors. One vector is this one, the second vector is this one. Okay, so I will find the determinant of these 2 vectors now. First vector in first column, second vector in second column. So if you find the determinant, it's 15 minus 0. So that is 15. So that is my area. So area of parallelogram that is given to me is absolute value of the determinant, but it is already positive, so I can just pick it. Let's say if this answer was negative, negative 15, I will just make it minus, will become plus. So we take the absolute value at the end. If it is already positive, no need to take the absolute value, because positive value gives you positive absolute value, no issues. Okay, so that is your area of parallelogram.
Sir, will we have this in the exam?
You asked me, so I answered.
Okay. Thank you.
So when I was going to chapter 5, you should have let me go. Right?
Master, you're number one.
X. What do you say? Act smartly, you know. So, person who's asked me this question, is it clear now?
Yes, thank you.
Okay. Parallel program. Okay. So basically, in in chapter 5, there are 3 types of questions that can be asked. Eigenvalues and eigenvectors. Basically, we write lambda for eigenvalues and eigenvector is V, right? So for any matrix A, if you multiply A with V and it gives you a number times V, then we call this lambda number as an eigenvalue and this vector V is corresponding eigenvector. So this is a relationship that we are looking for. So because we don't know at the beginning, so what we do first, we just write A into X equal to lambda X instead, because whenever we solve a system, we write X for unknown vectors, right? You see, even in the Cramer's rule, what we have, AX equal to B, right? So X is basically my unknown thing. So here, if I bring it to the left, we can write it as AX minus lambda X equal to 0. And because XX is common, I want to take that as common. A minus, but I cannot write just lambda here. If I write A minus lambda, it is not defined. A is a matrix, lambda is a number. I cannot subtract a number from a matrix. Only a matrix can be subtracted from a matrix. So we write an identity here, A minus lambda IX equal to 0. Now it's good. So X will be an eigenvector if this system, this is a homogeneous system. See, the right hand side is 0. If this system has non-trivial solutions, non-trivial solution X for any lambda, right? Any constant lambda. If this it has a non-trivial solution means X not equal to 0. A non-zero solution, because 0 always satisfy this one. If you take A into 0, this is always equal to lambda equal to 0 because they both become 0, 0. So we are not looking for 0. So this is not what we are looking for. Look, we are looking for some non-zero vector X that gives me the equal value for AX and lambda X. So from here we got this so this has a this system homogeneous system has non-trivial solution for lambda if and only if your A minus lambda I is non-invertible. If there is no inverse for that, then we will have a non-trivial solution. If it is invertible, I will only have a 0 solution. Non-invertible means the determinant of this has to be equal to 0, right? If the determinant of a matrix is 0, it is non-invertible. So this is the condition which we have for lambda. This is called the characteristic equation of A. Characteristic equation of a matrix A. Okay, so if you are given a matrix A, if this is a given matrix, and someone asks you what is the characteristic equation, basically you have to write that. And this characteristic equation is a polynomial equation in lambda, because when you solve it, it gives you a polynomial equation in lambda, like lambda square, right? Lambda plus c equal to 0, if it is 2 by 2. If it is 2 by 2, I will get a 2 by 2 second degree polynomial. If A is 3 by 3, then I will have a cubic equation. Right? So it will be quadratic for 2 by 2, quadratic equation. If it is 3 by 3, you will have a cubic equation. So this is what I was writing. So in 5.2, basically, they gave me this characteristic equation. In 5.1, they defined eigenvalues and eigenvector. In 5.1, they gave you one of the things. Let's say if lambda is given, right? Can we find eigenvector v? This is one question. Or if v is given, right? Can we find lambda? These two different questions are there. Second one is very easy. If v is given, what you will do, you will just multiply a with v. You will multiply vector with matrix with a given vector. You will simplify, you will get a vector only. Now try to write some lambda outside, which gives you your vector v back. So if you get your vector v back, you started from v, you got your v back, but along with a number lambda here. So that number lambda becomes the eigenvalue, and it shows that v is an eigenvector. So if your v does not come back, then it is not an eigenvector. So see here in example, if your vector is given, you see here the vectors are given, you multiply your matrix with a vector. If it gives you your vector back along with a number, we will say that yes, u is an eigenvector and the corresponding eigenvalue is -4. And if it does not give you your vector back, it means the given vector was not the eigenvector. So we cannot give you the eigenvalue. So this is a very simple question, the first one. But the second, this one, if lambda is given, then it's not easy to find the vector, because now if a is given, then a minus, let's say this lambda is given, whatever value of lambda is given, you can put that lambda here and you have to solve this thing for x. You will solve it for x. So for solving it, I can just write this a minus lambda I, which becomes a minus lambda, b, c, and d minus lambda. We only subtract lambda from the diagonal. You are subtracting lambda from the diagonal only. B and C don't change. And you try to make it 1001 form, right? But because it determinant is 0, it will never give you 1001. Give me a second, the battery is down. All right. So why you will never get 1 here? The reason is your matrix is not invertible. If this is the eigenvalue, then a minus lambda I is not invertible. You will never get 1. You will definitely get 0, 0 in the second row. So from here, you can write your solution. X1 is equal to negative star x2 and x2 is free. So if lambda is given and you have to find the eigenvector, then you have to solve this system here. You see? Show that 7 is the eigenvalue of the matrix A. So you have to basically solve the system A minus 7 I x equal to 0. So I will only write A minus 7 I, which is subtracting 7 from the diagonal. No need to write all this. You can directly write this. 1 minus 7, 6 and 5 don't change, and 2 minus 7. So now if you make it reduced echelon form, you see 1 minus 1 and the second row becomes 0. Second definitely will become 0. And from here, you can write your vector. So 1 and 1 will become your eigenvector. So finding eigenvector is the same that you do later on in 5.2 as well. Okay. So if a vector is given and you have to show that it is an eigenvector, it's an easy question. You just multiply a vector, right, matrix by a vector and see if your vector comes back or not. Then it is an eigenvector and it gives you the eigenvalue right there. Okay, but if lambda is given and you have to find x, then you have to solve the system and at the end you will get the value v. So usually if x2 is free, let's say you write x as x1, x2, whatever x2 is that minus whatever number you got here with x2 and x2 is free, you will take x2 common, you will get a number inside 1 here, right? So just drop this x, whatever you get here, that is your eigenvector v. Just write v as this given vector, whatever number is that. So in that example, it became minus 1 and 1. In 5.3, you see here it is a characteristic equation. I think that is given in 5.2. Characteristic equation is used to find the eigenvalues. Okay, and once you find the eigenvalues, we know how to find the eigenvector. So let me go in detail and do one of the problems. 3 minus 2, 1 minus 1. Let's say this one. Find the characteristic polynomial and find the eigenvalue. So even if they don't ask me the characteristic polynomial, if they only ask me find the eigenvalues, I have to write the characteristic polynomial. Without that, I cannot find eigenvalues. So 3 minus 2, 1 minus 1. Right? So first of all, I will write determinant, or first of all, write a minus lambda I. A minus lambda I means subtract lambda from the diagonal. Off diagonal do not change. Right? So that is your lambda. Now I will find the determinant of a minus lambda I and put it equal to 0. So it means determinant of this 3 minus lambda minus 2, 1 minus 1 minus lambda equal to 0. So now if you take the determinant, you have to multiply this and subtract that. So if you multiply, you will get lambda square minus 3 lambda plus lambda minus 2 lambda, and then 3 into 1 is minus 3, and minus 3 plus 2 is minus 1. You can write everything before, don't do the shortcuts. 3 minus lambda minus 1 minus lambda, and then minus 2 into 1, which is minus 2, equal to 0. So if you do, this is your characteristic polynomial. So if you simplify, this is the characteristic polynomial which they are asking me. So first find this equation, call it characteristic polynomial. So we got the characteristic polynomial. Now I will solve this to find lambda. So we know that if there are factors, I will make factors. If there are no factors, I will use the quadratic formula. So I think no factors are here, right? So I can use the quadratic formula. Quadratic formula says that minus b plus minus square root of minus b square minus 4ac divided by 2a. So that becomes 2 plus minus 4 plus 4, 8 divided by 2. So we got 2 plus minus 4 2s are 8. So it's 2 square root of 2 by 2. So if you divide by 2, you got 1 plus minus square root of 2. So these are the two eigenvalues. So you can say that lambda 1 is 1 plus square root of 2 and lambda 2 is 1 minus square root of 2 are two eigenvalues. So in this question, they did not ask me to find the eigenvectors, right? Just the eigenvalues. So we got the characteristic polynomial, we got the eigenvalues. So this was the only question here. This was 5.2 question 3. Question number 3. So if they ask you to find the eigenvectors, then you will do one by one. Okay. So I think they gave us in the first one in 5.1, you will see I will ask you both together. So here you see the eigenvalues are given and they are asking you to find the eigenvectors. So of course you can do that. For example, here the eigenvalues are 1 and 5. So if you know the eigenvalues, let's say 5.1 number 9, I can continue with this example, but these eigenvalues are not very good. 1 plus square root of 2, 1 minus square root of 2, it will become little difficult. It's easy to find eigenvectors if your eigenvalues are whole numbers. So I will also give you something with whole numbers, not with 1 plus minus square root of 2. So 5021. So ninth problem in 5.1. Let's say if this matrix is given at the beginning, you can 5021, you can find the eigenvalues 1 and 5. If you find the eigenvalues here, if you write determinant of a minus lambda I, put it equal to 0, whatever polynomial you are getting, solve it, you will get lambda 1 and lambda 5. Okay, so they gave you, but definitely it's not difficult. So now one by one. So for eigenvectors, what you will do? For eigenvectors, you will go one by one. So first you will take lambda equal to 1, the first one, right? So I will solve a minus 1i, lambda was 1. A minus 1i x equal to 0. So I will solve this thing for x. Okay. For characteristic polynomial, we solve it for lambda, right? Characteristic polynomial, we solve it for lambda. There is no x1, x2. There is just lambda. But now we have x1, x2. So I will only consider a minus 1i. I will not write the whole system. I will just write the, if you want to write augmented matrix, you can write that. But I think coefficient matrix is enough. So 5 minus 1, 0, 2, 1 minus 1. Right? We subtracted 1 from the diagonal. So it becomes 4, 0, 2, 0. So if I make this 1, if I make 1, 0, 2, 0, means divide the first row by 2. Now use 1 to make this 0. So I can do R2 minus 2R1. So if I do R2 minus 2R1, you will get 0, 0. So see, the second row has become 0. But here you got x1 equal to 0 and x2 free. X1 plus 0, x2 is equal to. So the first equation basically gave you x1 plus 0, x2 equal to 0, right? So this means your x1 is 0 and x2 is free. Now if you write the vector x1, x2, your x1 is 0 and x2 is free, so it remains x2. If you take x2 common, it becomes 0, 1. So what I will do, I will only pick this vector. Therefore, v1, the first eigenvector, is 0, 1. I will only pick this one, you see, 0, 1. Okay, so this is the eigenvector for lambda 1 eigenvector for lambda 1 equal to 1. So for first eigenvalue, I got first eigenvector. For second eigenvalue is lambda equal to 5. So I have to solve now a minus 5i, a minus lambda I x equal to 0, and we are solving it for x. So now I will write a minus 5i. A minus 5i means subtract 5 from the diagonal. So that is 5 minus 5, 0, 2, and 1 minus 5. So you got 0, 0, 2, minus 4. If you change row 1 and row 2, you will get 2 minus 4, 0, 0, and divide row 1 by 2. You got 1 minus 2, 0, 0. So no need to for any other operation. This is a reduced echelon form. So now if you write x1 minus 2x2 equal to 0, see, x1 minus 2x2 equal to 0, and second equation does not give me anything, so x2 will be free. So x1 is x2 and x2 is free. One of variable has to be free. Now if I write the answer, which is x1, x2, x1 is 2x2, x2 is x2 because it is free. So I will take x2 common outside, so I will get 2, 1. So now I will only pick this one. Hence my second eigenvector v2 is 2, 1 is the eigenvector for the second eigenvalue, which is 5. So this is the eigenvector for lambda 2 equal to 5. So this is in 5.1, 5.2. So if a matrix is given, you can easily find eigenvalues and eigenvectors. After that, one thing that we studied, it is a just one step thing, which was 5.3. 5.3 was a diagonalization. Diagonalization is, if A is given, can we write A as PDP inverse? That is diagonalization, where D is a diagonal matrix. So if you have eigenvectors and eigenvalues, you can write this D. Your D will be lambda 1, 0, 0, lambda 2. Or continue. If there are more eigenvalues, then more diagonal. So eigenvalues on the diagonal, and your P vector has eigenvectors as the columns. Just one step. So in above example, which we just did, right, my D will be 1, 0, 0, 5, because 1 and 5 are two eigenvalues, and P is the first eigenvector, which is 0, 1, and the second eigenvector, which is 2, 1. So if we just replace lambda 1, lambda 2 on the diagonal and v1, v2 as the columns, these are your D and P. Diagonalization means writing A, right? So we can easily write. Now, if you want to check whether it is true or not, you can multiply A with P and P with D. They will both be equal. If you multiply A with P and if you multiply P with D, they both will be equal. Okay, if they are equal, it means AP is equal to PD. Now if you send this P on the other side, your A will become PD P inverse. So no need to find the inverse. If we just show that AP and PD are equal, that is enough, because it automatically means that your A is equal to PDP inverse. So it's very easy to check. Let's say if I ask you find the eigenvalues, you find the eigenvalues 1 and 5, then find the eigenvectors now. So you found the eigenvectors for lambda 1 and lambda 5. Now in the third step, if we ask you write the matrices D and P such that your A is equal to PDP inverse. So just in one step, you will write D and P. And if you want to check, of course, you can check if they are equal. It means everything that you have done above is correct. So this is the only thing in chapter 5 that can be asked. Okay. In 5.5, we did complex numbers, complex eigenvalues, but only real eigenvalues is enough from chapter 3. Okay. So I will ask you the question just from 5.123. Complex eigenvalues are not different. Methodology is exactly the same, but we will play with complex. When you find this quadratic formula, here you get a minus inside the square root. Sometimes what happens that you get minus in the square root, then it gives you complex eigenvalues. So that's it from 5. So what else we have? We have vector calculus, vector, and complex numbers. So let's say if I go through, and there was this, these are the vectors. So if vectors are given, how to find dot cross products, I think these are easy things. Nothing much is there. Do you want to see anything from here? Vectors were not difficult.
Yes, Mr.
What exactly? So if A and B
Master,
are given,
just give us general revision,
okay.
please. Thank you.
So let's say if you have A and B, two vectors. For example, here in this exercise, you have 1 minus 2, 2, and 2 minus 1, 2. One minus 2, 2. And 2 minus 1, 2. So basically, you can add, subtract, that's not an issue. If you add I in I, j in j, k in k, right? So for example, here they're asking you a plus b, a minus b, 2a. That's not a problem. Dot and cross product. So in a dot product, what you do, you multiply the coefficient of I with the coefficient of I. So here it is 1, you multiply 1 with 2, 1 with 2, and plus, you multiply j with j. And the third one is this 2 with 2. So no ijk here. In dot product, no ijk. Just multiply. If you have a1i, a2j, a3k, and b1i, b2j, b3k. So you will multiply just a1 with b1, a2 with b2, a3 with b3. That's what we did. And it will be a number. So now 2 plus 2, 4, plus 4, 8. Right? So that's always a number, a scalar. Dot product of two vectors is a scalar quantity. Cross product of two vectors is a vector quantity which is defined like this. You write ijk in first column, then coefficients of A, components of A, 1, minus 2, 2. You see, components means coefficient of I, 1, minus 2, 2. And the second one has 2, minus 1, 2. Now you find this determinant, it gives you a vector. So first one is this one, right? This is gone. So you got this minus this. So I will give you minus 4 plus 2, right? And then minus, this is second one, minus, this is gone, this is gone. So you'll get this with 2 and this with 2. So minus j will give you 1 into 2 is 2 and minus 2 into 2 is 4 and plus k, right? So k is this third one, so this is gone now, right? So you got 1 into minus 1 and 2 into minus 2. So you got minus 1 plus 4. So here your vector becomes minus 4 plus 2 is minus 2 with I, and this minus minus plus 2 with j, and 3 with k. So see, this is a vector. So when you take a cross product, it gives you a vector. So these are simply dot and cross products. In the second part, they said find the angle between A and B. So angle between A and B has this formula. Cosine of the angle between them is A dot B divided by A magnitude and B magnitude, the length of A and B. We just found A dot B. A dot B is 8. And if you want to find the magnitudes, you can do it here. The magnitude of A is equal to A square plus B square plus C square. We take the square of all. So 1 square plus minus 2 square plus 2 square. So that is 4 plus 4 plus 1, 9. It is 3. And for B, the magnitude is 2 square plus minus 1 square plus 2 square. So that is also 9. So that is 3. So both lengths are 3 and 3. So you got 8 by 9. So hence the angle between them becomes cosine inverse 8 by 9. Of course, I need theta, right? So I can send cosine on the other side. It becomes cosine. So now you can use calculator and write the angle between them. If you use calculator, cosine inverse 8 by 9, it will give you some answer here. So that will be the angle between two vectors. So dot product basically gives you the angle between two vectors. If these are A and B, so the angle between them is theta. Cross product also gives you the area of the parallelogram. See, we took the cross product of we saw that the determinant of two vectors, if two vectors, these are the two adjacent vectors, A and B, the area of the parallelogram is also obtained by the absolute value of the cross product. So if you find the length of this vector, it gives you the area of the parallelogram. So this was the vector, right? A cross B. So if you find the magnitude from here, this was A cross B. So if you find the magnitude, it will become 4 plus 4 plus 9, square of all. 2 square, 2 square, 3 square. 17. So this is the area of the parallelogram. Okay, so very easy formula. These are three things related to the functions. If a scalar function is given, this is a scalar function because no I, j, k is there. We can find the gradient of the scalar function, del phi. Find the gradient of phi, which is del phi. Divergence of a vector function. You see, this function is a vector function. Why vector function? Because it has I, j, k in it. You see, I, j, k. So divergence and curl, they both are defined for vector functions, and very simple formulas, just it needs some of the derivatives. For example, if a scalar function fx, y, z are given, I can find three derivatives here. The derivative of phi with respect to x, the derivative of phi with respect to y, the derivative of phi with respect to z. These are called partial derivatives, right? So when we take the partial derivatives, we keep the other variables fixed. For example, the derivative of this function with respect to x will be 3x squared from here. It will be 0 for y cube, 0 for z cube because there is no x. And here 3yz are constant, the derivative of x will be 1. So it will become 3x squared minus 3yz. Similarly, derivative with respect to y will become 3y squared minus 3xz and so on. So finding the partial derivatives is not an issue, and we find these derivatives and put in the formula. Gradient of phi is a vector which takes the x derivative with I, y derivative with j, and z derivative with k. So if you find all these derivatives and put them here, it will give you the gradient of the function. If a vector function is given, vector function has some function with I, some function with j, some function with k. So there are three functions basically here, f1, f2, f3. If you want to find the divergence of f is called del dot f. When you take the dot product, there is no ijk. So you take the first one, f1, with x, second with y, and third with z. Now you are not taking the derivatives of all the functions with all variables. No. F1 with x only, F2 with y only, and F3 with z only. Simple as that. So if you have this function, this is your F1. So you will just take the derivative of x1 with x. This is your F2. You will take the derivative of this with y. So for example, here the derivative, this is your F1. This is your F2. This is your F3. So you just take the derivative of f1 with respect to x. F1 with respect to x. It will be 4. The derivative of x is 1 and y, z are constant. 4 and y, z constant, the derivative of x will become 1. You will take the derivative of f2 with respect to y. So this with respect to y, and z is constant. So y square becomes 2y and z remains there. Similarly, partial f3 by z. F3 by z. Now y is constant and z square becomes 2z. So this will also become 2y. Now, if you find the divergence of f, it is f1 with xi, f2 with yj, and f3 with yk. That is your divergence of f. So this will become f1 with x. F1, this one. So 4yz with I. Then 2yz with j. And 2yz with k. So this is your divergence. If any point is given, then I can put the point here as well. Let's say if they ask you what is the divergence of f at 1, -2, 3, right? So it means x is 1, y is 2, z is 3, right? Y is 2, z is 3. So just put the values if some value is given, right? And get the answer like that. Is f solenoidal? F is solenoidal if divergence is 0. If the divergence of f is 0, we call it solenoidal. But here divergence is not 0, right? So it means f is not solenoidal, right? So answer will be no, because the divergence is not equal to 0 in our case. The curl is the cross product. You see, if you want to find the curl of f, it is the cross product, del cross f. Dot gives you divergence. So I will write ijk, and del means the derivative with respect to x, derivative with respect to y, derivative with respect to z. And f means f1, f2, f3. So you will do that. So in this example, if you write ijk and partial by partial x, partial by partial y, partial by partial z, and f1 is this, f2 is this, f3 is this. Resume. Okay, so f1 is sine y plus z. F2 is x cos y minus z. And x minus y will be in there. So now we all know that how to find the cross product, right? We just take this I, remove, multiply. Multiplication means take the derivative of this with respect to y. Partial by partial y of x minus y. Then partial by partial z of this. Similarly, when it's j, partial by partial x of x minus y. Partial by partial z of sine y plus z. For k, this minus this. So these are the derivatives basically with I, with j, with k. So curl will be a vector. Curl will be a vector. Divergence is a scalar. I think I should not write ijk here. Why I wrote ijk? Divergence is a scalar, so there is no ijk, right? For the divergence. It's better that I saw that, otherwise you must be confused here. There is no ijk. Okay. So it is just a scalar, because divergence is partial f1 by x plus f2 by y and f3 by z. There is no ijk by z. So we got this value. So we can add, basically this becomes 8yz. 4 plus 6 plus 2, 8. So my divergence is just this. 8 into y into z minus 48. Okay. So in divergence, there is no ijk. In curl, there is ijk. And if curl is 0, then f is irrotational. F is irrotational if curl is 0. So if you find the curl and it comes out to be 0, you will say that yes, f is irrotational. And if curl is not 0, it is not irrotational. Whenever you have a flow of anything and it is rotating, then curl gives you the rotation of the flow. And if some flow is just straight, there is no rotation in it, curl of that flow will be 0. Okay, so that's pretty much it in this section. So let me write curl here as well. So two things that we got from here, divergence and curl. Divergence was del dot f, curl is done. Cross F. So don't multiply these two things. These are the derivatives. So F1, F2, F3 will get differentiated when you use. So partial by partial of y of F3 minus partial by partial z of F2. That's how you write. Partial F3 by y minus partial F2 by z. So it's not a multiplication. These are the derivatives. Then with j, x of F3. F3 with x and minus z with F2, F1. This will be j. And then plus k. K will give you x, F2 and F1y. F2 with x and F1 with y. K. Okay, so that's how you can find the divergence and curl. So in complex numbers, I think complex numbers was so easy. Important things are whatever complex number is given, there are some things are related with them. Complex number is x plus iota y, where x and y are both real numbers and iota is defined as square root of -1. Or you can say that iota square is -1. Whenever numbers are written like 2 plus 2 iota, -1 plus 3 iota, 7 minus 6 iota, right? These are all complex number because there is iota with them. It's not the I vector that we have. That was the I vector in the direction of x, I vector. But here in complex number, I is an imaginary number which we call iota, an imaginary number, imaginary unit, you can say that. Real unit is 1, imaginary unit is 1 iota. So if z is that, z conjugate is x minus iota y. So if you just change the sign of iota, it becomes conjugate. Iota becomes minus iota, it is called the conjugate of z, right? Then we have a modulus of z. Modulus means z mod, that is x square plus y square square root. Okay. Then we have an argument of z. Argument is written as a or g of z. That is called tangent inverse y by x. If you divide this y by x and take the tangent inverse, it gives you the angle basically. So a complex number is always written as this. If this is your x and this is your y, then we call this point xy, and we can call this vector from origin to xy as z. So this is your complex number z. Basically, it has a length which is called r, and it has an angle with x-axis which is called theta. So basically this r, the length is the modulus of z, which we found here, and theta is the argument of z that we found from here. Okay, so modulus and argument gives you r and theta, and once you have r and theta, then you can write z as this. Z can also be written as r cos theta plus iota sine theta. If you put this r, whatever you get here, and put this theta, whatever you get here, right? This is called the polar form of z. So it's very easy to find the polar form of z. You just have to find r and theta. So if you look at this one, write the following complex number in polar form. So let's say if z is this one, minus 3 plus 2 iota, minus square root of 3 plus 2 iota, right? So see, they said write it in the polar form. So it means first I need r. R is the mod of z. Mod is minus square root of 3x square plus y square. So x square is 3 and y square is 4. So 3 plus 4 is 7. This is 7, right? And then theta. Theta is tangent inverse, argument of z. This is called argument of z, which is tangent inverse y by x. Y is 2, x is minus square root of 3. So if you use calculator, it will give you some angle. But you have to be very careful. Calculator only gives you the angle in first and fourth quadrant. Means if this is positive, it will give you the angle in first quadrant. If this is negative, it gives you the angle in fourth quadrant, negative theta. Okay, for example, here 2 by square root of 3, this will give you a negative angle. But your complex number may not be in the fourth quadrant. You have to be careful. If I write tangent inverse 2 by minus square root of 3, I'm writing this in calculator. Minus 2 divided by square root of 3. So this gives me almost 50. Angle is almost 50, minus 49.10. So almost minus 49, minus almost minus 50 degree, right? So see, they gave me the fourth quadrant. But if you look at this complex number is here. Minus square root of 3 is 1.73, right? So minus 1.73 is somewhere here. And 2 is 1, 2. 2 is somewhere here. So see, it is in the second quadrant. This complex number is in the second quadrant, minus 3 and 2. But they gave me exactly the opposite, 50. They gave me this minus 50. This is not correct. So my angle is this one, starting from here to here. Instead of going to this, you went opposite side 50 degree. It means now I have to come back from there. So I have to add 180 degree. 180 degree. So this will not be the correct angle. Plus 180 degree, which is 120 degree, will be the correct angle. So this is actually, you have to be careful. 180 minus 50 is 130, right? Not 120. So this is my correct angle. So now if you write the polar form of z, it will be r into cos theta plus iota sine theta. R is square root of 17 cos 130 plus iota sine 130. This is the polar form, required polar form. Now, if they ask you to take any power, let's say, here you see, they said, this is the vector, find R20. So it's very difficult to find R20 directly. So what we do, we write Z as a polar form and then use De Moivre's theorem. So let's say in this question, let's say if they ask me to find Z to the power, any power, let's take Z to the power 50, let's say. Then it is square root of 17 to the power 50 and then cos 130 degree plus iota sine 130 degree to the power 50. De Moivre's theorem says that if you have cos theta plus iota sine theta, just bring the power with theta. This is the De Moivre's theorem, which is very helpful. So De Moivre's theorem says that this becomes 17 to the power 50 into 1 by 2 will become 25 cosine 50 into 130. So De Moivre's theorem brings this power with the angle sine 50 into 130. So this is the De Moivre's theorem. This is called De Moivre's theorem. It brings the power down with theta. So whenever you have a polar form, it's very easy to take the power of a complex number. So now if you multiply 13 into 5, whatever your answer is, and you can simplify. Okay. In other problems in complex number, which were given here, see, you have to simplify. If you are adding complex number, you can add 2 in 3 and 5 in 4. Very easy. If you are multiplying, you have to multiply everything. 1 with 2, 1 with iota, 2 with 2, 2 with iota, like that. So for example, it is 1 with 2 is 2 and 1 with minus iota is minus iota. Then 2 with 2 becomes 4 iota and 2 iota with minus iota becomes minus 2 iota square. And now iota square is minus 1. So this becomes plus 2. So 2 plus 2 becomes 4 and minus iota plus 4 iota becomes plus 3 iota. So see, whenever you multiply two numbers, you again get a complex number, x plus iota y. Similarly, if you are dividing two numbers, right, whenever you divide two numbers, you multiply and divide by the conjugate of the denominator. Just change this 2 minus 3 iota to 2 plus 3 iota, 2 plus 3 iota. Why we do that? Because at the top, I will have a multiplication, which I can do very easily, right? I just did this multiplication, but in the denominator, it becomes a square minus b square. Iota square is minus 1, so it becomes 4 plus 9, 13 in the denominator. You see, so there is no more iota in the denominator. That's why we multiply and divide by the conjugate of the denominator. Conjugate of the denominator, you see. Why? Because when you multiply any z with its conjugate, it becomes x square plus y square, which is the mod of z square. So no iota is there. This is the benefit of multiplying z by its conjugate. And now at the top, you can just multiply 3 with 2, 3 with 3 iota, 5 with 2, 5 with 3 iota. So you will get a complex number here divided by 13. So that will be the answer. Okay. And we know how to find the modulus, how to find the argument. So this is all easy, I think. So I think that's pretty much it. I think I went through almost everything in the topics. Okay. So hope this will help you. Try to go through the exercises, whatever are left, what I left halfway done. Try to complete them and see if you can do extra work. Of course, they will help you. So it's a long video now. Let me stop the video.